formation of of stars like our sun. And it's going to go through 7 steps here. So, stars, like our sun, form when interstellar medium collapses under its own weight, right? Just like I said, the nebula, there it was, it starts to collapse. So what starts to collapse it? Well, there's a fight heat, and once this nebula starts to clump enough, right, it starts to get that more dust than gas, I guess, gravity starts to win. And so it starts to collapse. And again, I like putting this in because we don't know why that actually starts. What triggers could that be? Well, like I said when I first introduced that theory, don't really know. So these are some ideas. Collision of gas blobs, right? So the gas starts forming into dust, bigger things, more gravity, gravity wins. Could have been a shock wave from some other star forming elsewhere. And so, again, it would kind of send a shock wave through, which would allow the heat to minimize and the gravity to increase. I'm not sure. Creation of an emission nebula. Again, some sort of disruption in the equilibrium, allowing gravity to take over. A supernova nearby. Or the cloud's cooling. Right? Well, if the cloud's cooling, then there's not as much heat to fight the gravity, and gravity. Just some ideas of what we think could have happened, and the nebula starts to go. All right, so to become something like our sun, there's 7 stages it has to go through. And each of these stages has to take into account temperature, surface temperature, density, and radius. Okay, and here's just a chart of the stages. Stage 1, interstellar cloud. Right, so you have the dense interstellar cloud, right? And again, it's a vacuum, but it's the dense interstellar cloud. Contains 1,000 times more mass than the sun actually has. And it's big, right? We talked about these. And they can be very, very big. They're cold. And so just enough heat to maybe escape and let gravity starts. And you start taking those gas and dust and form small little clumps. So just kind of like we talked about with the solar system forming clumps, right? That's what I mean. So you start getting those and you start getting a little bit more clumping. Right. Now, no star is born in isolation. This is interesting because we've talked about there's stars in groups, there's stars in binary systems. No stars are born in isolation. Yet our star is isolated. And so fragmentation stops when the gravity is so strong that the heat cannot escape, heating up the interiors of the clumps. So that's where we get to at the end of stage 1. Stage 2, the contracting cloud. Right, so the cloud's getting smaller. It's starting to shrink. Fragmentation is stopped, only in the interior cloud, but heat still can escape from the rim of this cloud. Right, and we go from tens of kelvins to 100 Kelvin. So we get warmer inside this cloud. The clump continues to shrink until it becomes the size of a solar system. Now, because we're talking about our sun, stars form like our sun, we can say our solar system. But stage 3, the interior of the cloud is now 10,000 degrees Kelvin. So we went from tens to 100 to 10,000, right? And it's starting to look like what might be considered a star. Right? You can kind of see maybe like the little orange thing and some blues, right? So this is what we call a protostar. And you can see it's protosphere. So stage 4, we are officially a protostar. This is 100,000 years after fragmentation. We are now at 1 million degrees Kelvin. However, there's no nuclear fusion yet. That's kind of a key, okay? And the size of the cloud is the size of Mercury's orbit. So still big. I mean, not big compared to what it was. It's kind of tiny. Still big. And the whole thing is 1,000 times brighter than the sun. And look at this next line. Can be plotted on the HR diagram. So we finally started to plot this on the HR diagram, and we'll be able to track its life throughout this diagram. All right, so there it is, right? Stage 4. Right. It's big, 100 times that of our sun in radius-wise. It looks like it's going to be one of the denser things, right? With the probably an IB or maybe a II, right? And then you can kind of see the picture here as it contracts. So stage 1, giant, scary looking thing. Stage 2 kind of looks more spherical. Stage 3 and stage 4, you've got kind of like a spinning with jets coming out of it. And then stage 5, which we're going to get to next, that looks more like a galaxy, a sun, a solar system. I'm not sure. All right, so stage 5, Protostellar Evolution. So we're still contracting. We're not contracting as quickly, so we've slowed down a little bit. And we've also shrunk. We're 10 times the size of the sun. Our surface temperature is 4,000 degrees Kelvin, but the interior is 5 million. Right? 10 times more luminescent, more brighter than our sun. However, still no fusion. Okay? And we're starting to get jets come off of this disk. We're almost at a start, no fusion yet. And again, we can be plotted on the HR diagram. Just take a quick look at the HR diagram here. We got 4, 5, then you got 6 and 7. But we just talked about 5. Now we're moving on to 6. 6, we are a star 10 million years after stage 4. Right? And why are we a star? Nuclear fusion has begun. Now we are still contracting. Our radius is huge. Our surface temperature is 4,500 degrees Kelvin, but the central temperature where the fusion is 10 million degrees Kelvin. And lastly, stage 7, 30 million years after stage 6. Just a little bit of time. Surface temperature about our sun, right? 6,000 degrees Kelvin. Central temperature, again, our sun, 15 million degrees Kelvin. Right? The star is now at equilibrium. We are no longer contracting. Good news, this star, our sun, will remain unchanged for the next 10 billion years. We're about half that. Good news.